Okay, so we are gonna actually get started with this chapter today. This is time series analysis in Python here. So time series is absolutely one of the most important and also the widely, commonly actually used like techniques in a lot of like fields in finance, stock price prediction, and also other kind of time series seasonality prediction. So today we are gonna kind of like give you guys some kind of introduction on the time series analysis. So we mainly have four different parts. So the first part is just some kind of introduction with the basic definitions and also some kind of metrics we can use to evaluate the time series models. The second part would be the techniques to actually do the moving average, the smoothing techniques, and also the evaluation metrics for the time series. For example, like the rolling windows, exponential smoothing, and triple or hot winters model for smoothing, and some kind of cross validation and parameter selection for the evaluation part. Then the next part is some econometric approach. This is also, I think this is also the hardest part. So for a lot of time series model is not perfect, we will have some kind of problems like non-stationary problems. So this kind of section is telling a story about how to actually solve this kind of wide range of different problems and how to construct a kind of like rigorous and also very convincing model, time series model. The last part would be some kind of like a trial to actually build a model, a time series model, use a feature extraction and a linear model, and some kind of like a regularization for the feature selection. And the last part will be just like kind of improvement. What if we just switch from linear regression to actually boost? What kind of improvement can we get from that? So the first two part will be handed over to Shupei and Wang Yu. So the first part is actually going to be covered by Shupei. So I will just hand over to Shupei now. Okay.
So can you guys see my screen with the notebook shared? Okay, so now let's get started. So let's begin with a simple definition of time series. Time series is a series of list of data points in time order. So if the data is organized by timestamps and compared to random sample data, it may contain additional information that we can extract. So let's now import some of the packages that we're going to use in today's time series modeling. So first, we're going to import NumPy, pandas, matplotlib.pyplot, and then SIB1. And then we're going to import relative delta from date util. This is a package for the extension of the datetime module. And then we're going to import stats model. For those of you who are familiar with R, this stats model would be very familiar to you. And then, so now let's get started. So first, we will git clone the repository of the ML course on GitHub. And then we'll pull out the ads data and then the currency data. These two sets of data are the ads watched per hour and then the currency spent per day and at a real mobile game. And now let's pull out these data. And then first we will plot the ads data. So it's ads watched per hour, and then we can see that we can see that there is a trend of going up and down in this figure, but we don't know what this means yet. And then now let's plot the figure of the currency spent per day in this game. And then in this figure, we can also see that for a certain amount of period, we can also see there's a peak going up. Now let's, before we begin forecasting, let's understand like how to measure the quality of our predictions and take a look at the some of the metrics that we're going to use. So the first metric is the R squared. It's so R squared is defined as 1 minus the sum of squared of the difference between the actual value and the predicted value over the sum of the total difference between the actual value and the mean of this sample. And then we can use scalar metrics to import this metric. And then the next one is the mean absolute value. It's the sum of the absolute value between the y, well, or in our case is the variable. Sorry, what is the question? How much y can be explained by x? Oh, okay, no problem. So it's just for the mean absolute error, it's just the sum of the difference between the absolute value of y1 and the actual value minus the predicted value. Sorry. And for the median absolute value, again, it's just a metric. So the absolute, the median of the actual value minus the predicted value, and then so we take the median of the whole sample, and then so this metric is very interesting that it can sort of ignore the effect of outliers, since it's just considering the median. And then the next one is the mean squared error. So this is the sum of the squared of differences between the actual value and the predicted value divided by the number of samples. And the mean squared logarithmic error is just, well, this is somewhat similar to the idea of mean squared error, but it's just in a logarithmic scale. And the next one is the mean absolute percentage error. This is the same as the mean absolute error, but just in the form of percentage. And then so we've covered like the metrics mentioned above. So now we're just going to use scalar metrics to import all these R2 score mean absolute error, and then the median absolute error, and then the mean squared error. And then since the mean absolute percentage error is not defined in the scalar metric, so we will define it here. So now we know how to measure the quality of our forecast. Let's see like what metrics we can use, and what we're going to do in our with these metrics in our modeling. So let's just start with the naive hypothesis. Tomorrow will be the same day as today. However, instead of a model like yt hat equals yt minus 1, which is the same as the tomorrow will be the same as today, we will assume that a future value of our variable depends on the average of its k previous values. Therefore, we will use the moving average. So we'll first define a moving average function. So this function is just kind of going to calculate the average of the previous n observations. So if we want to do a calculation on the moving average of the ads data for the past 24 hours to do a prediction, and then we can see that we get a value of around 116 to 17,000. But unfortunately, we cannot make predictions far in the future. So in order to get the value for the next step, we need the previous value to be actually observed. So the moving average in this case has another use case. It can be used to smooth the original time series to identify any trends. So in pandas, there is the implementation already available. So it's called the data frame dot rolling bracket window dot mean. So the wider the window, the smoother the trend. And so with this rolling window dot mean, it can help to identify any common patterns. So now let's define the plot moving average. In this function, the series argument is the data frame with time series, and the window is a rolling window size. And plot interval is just show the confidence of the intervals, the confidence intervals of the data. And then the plot anomalies argument will show anomalies, so just any outliers in the trend. So the rolling mean is calculated by series dot rolling mean bracket window dot mean, and then we plot the rolling mean, and then for the confidence intervals, so it's just showing like that how to say, it's showing a lower bound and upper bound of the data within this confidence interval. And then if you guys are sorry, we got a question. What's the rolling mean? So the rolling mean is the just calculating the mean for the past like certain amount of time. Does that explain the question? I'm not. Or we can.
Just a quick kind of like note here. So that's right. Rolling mean is actually a calculation over a specific window. But another kind of important feature is that lies on the word rolling. So basically, for example, if the window is 24, that means, for example, we have 24 hours. Then we're going to do the rolling mean from the first hour to the 24th hour. Then we're going to do the rolling mean from the second hour to the 25th hour, then to the third hour to the 27th hour, so on and so forth. So you kind of rolling. Every single window is like 24 kind of hour. You're kind of rolling by each unit. You're kind of pushing forward by one unit.
Yeah, that's correct.
Yeah. Okay. Go ahead, please.
So this lower bound and upper bound is just so if you guys are familiar with statistics, so how to explain this? So it just tells us that we are 95% sure that the rolling mean will stay in this range, and then we define how to find the anomalies. So that the anomalies is data points that either lower than the lower bound or higher than the upper bound. Don't worry, I'll show you guys later in. And then then we plot the windows. We plot the actual values and the moving averages. So now let's smooth by the previous 4 hours. We can see that if we only smooth the data by the previous 4 hours, we can see that the rolling mean and the actual values are actually very similar. If we increase the window, the rolling window to 12 hours, we will see that actually the rolling mean is kind of flattened by the increased window. And then we increase the window further to 24 hours. We see that the rolling mean is kind of, in the form of a straight line. But still, if we do the rolling moving average, we can see how the dynamics of the as data changed. But if we can see that in these figures, there's actually a trend that is changing. So probably during the weekdays, we get a lower amount of ads watched compared to weekends where we get higher ads watched per hour. And if we plot the confidence intervals, we don't see any outliers in our data. So now let's create a simple anomaly detection system with the help of moving average. So unfortunately, in our data, we don't have any outliers. So we'll just make one of the data as the outlier. So we will change the last 20th data points, and then multiply it by 0.2. So we decrease the amount of ads watched per hour by 80% of that for that data point. And then bingo, we see we identify our first anomaly here. And then for the second data sets, the currency data sets, if we plot the data, we can see that there are several anomalies in this data sets that are beyond our confidence intervals. It's not that these data are abnormal, it's just that this is a downside of our simple approach. It just marked all our peaks as anomalies. So if we want to avoid this type of problem, it's better to consider more complex models. So the weighted average is it's a very simple modification to the moving average. So the weights will sum up to 1 with larger weights assigned to most recent observations. So let's first define the weighted average function. So this function calculates the weighted average on series. So let's do a calculation of weighted average on the ads data sets. So with a series of 0.1, 0.5, 0.25, 0.15, and 0.1 assigned as the weights to the past 4 hours. So 0.5 will be assigned to the most recent hour, hour 4, and 0.5 will be assigned to hour 3, and 0.15 to hour 2, and then 0.1 to hour 1. And then we can see the weighted average is 91,700. This is the end of my part, and I will pass on to Yu Wang for explaining and discussing exponential smoothing and time series cross validation. I wonder if you guys have any questions.
Any other questions? Okay, Kempe, if you don't mind, can I just make some complimentary notes on your lecture?
Yeah, sure, no problem.
Yeah, okay, I will just share my screen here.
Sure.
Thank you so much, by the way. Okay, so pretty much like Kempe introduced like all aspects, like basically all the definitions like we need for time series here. I just want to make some quick notes on the some of like really tiny kind of detailed kind of concept here. So the first one here, I want to I want to talk about is this matrix here. So the R square is how much like y can be explained by x. So basically, this is commonly used for linear regression. The mean absolute error here and also the median absolute error are mostly used for the noisy data. So if you have some kind of like outliers, then this will actually cancel away with the summation here. So basically, if you have really noisy data, you're probably going to consider those two. Now this is just like ordinary least square we had before, and this one can be used when you have y equal to 0. If y equal to 0, that means here log would be 1 plus 0. So you won't have log 0 here. So this is most of the time, like commonly used when you have some kind of exponential trend here. That is y equal to 0 or greater than 0 over there. Okay. Sorry. So that's a metric part. Second, like the moving average here. So I want to say the moving average has two purposes. The first purpose is a prediction. So the moving average basically said your current t or your future t, like t plus 1, basically depends on the average of all the previous t time period y. Okay, so basically you can use all the time period before t to predict the next time period. Then you keep doing that. For example, here's yt equal to 1 over k, the summation of yt minus n. You can also do yt plus, since after you finish that, you get a yt hat, right? Then you can do it again for yt plus 1 equal to 1 over k, yt plus 1 minus n. Okay, so you can keep doing that for a prediction. Of course, this is a really sloppy kind of prediction because you only use the average. So that's one purpose. The second purpose is for smoothing, because sometimes, like Tianpei just showed us, this kind of data is really kind of like a noisy. It's kind of like a fluctuates like all the time. So we want to smooth the trend to make it like, to actually find like some, kind of precise kind of peaks or bottoms or downs over there. So that's when you're going to use a moving average. But this is actually based on the statistics. So basically, you have a hypothesis, which is H now here. So H now said your current Y or your future Y totally depend on the previous T time period or N time period average. So that's a now hypothesis here. So I just gonna write here. So H now here. H now is YT depends on previous and average Y. And H1 would be, no, that's not true. Otherwise, right? That would be otherwise. It doesn't depend on that. That he is here doesn't equal. So that's exactly why we actually use the confidence interval here. And that's exactly why we actually care about a normal kind of data points here. Why? Because think about the confidence interval. So suppose this is 95 confidence interval here, and suppose this is like a z test, normal test here, normal distribution. Here would be z negative alpha, right? And here would be that alpha here. Okay, so basically, if you're in this area, that means we don't reject H now, right? But if you're out of this area, you're out of the confidence interval, we reject H now. So basically what Tianpei just said here, like a lower bound and upper bound here, basically correspond to this and that, okay? So basically we're trying to construct like a really roughly speaking confidence interval for the data points here. So I'm not gonna actually, so basically this part to be specific, like a lower bound would be, I guess it would be like the y mean minus 1.96, which is the alpha times sigma over square root of n. I hope this can ring some kind of bell so that you can remember, this is like how we calculate lower bound, right? So for the upper bound, it's like opposite case. So that's how we got this part. Of course, this is not a traditional upper bound or lower bound. If you can't understand this, you're welcome to talk to me, in the chat. But I'm just gonna, roughly give you some kind of introduction right here. So basically, if you are in this area, that means you don't reject the H now here. That means, yes, YT does depend on the previous, like n average Y over there. So basically, that means your current model, your moving average model for prediction works. Okay, that works. But if you're outside this area, you are lower than the lower bound, which is here, or higher than the upper bound, then what does that mean? That means we're going to reject the H now. That means your model doesn't work at all. So you have to plot this graph to convince people that your model is working. Otherwise, you just tell me, oh, I just use the past average to predict the current YT. It doesn't make any sense. You need some kind of test. So this is like a graphical test to prove that it's gonna work. So if we just look at what 10 pages showed us right here, for example, in this graph, we don't have any kind of abnormal data points. That is, all the data points are within the confidence interval. So that is, we do not reject the H now. We do not reject the H now here. But if you look at these data points here, there are many kind of like data points which are outside the boundary. That means for this data, for the currency data, maybe this model doesn't work that well. Maybe it doesn't work that well. Okay. So yes, that's actually my kind of like a note for the moving average. Any question here? Anyway, so the point is like you can't just give me a model and tell me this is the model you use. It doesn't make any sense. You have to prove to me like this is the model that's gonna work. So basically, Tempe is showing all of us how the model gonna work by plotting different graphs right here. And also, the more larger window you have, the more like a larger space of the average you're gonna take, the more smooth the point like the curve is gonna be. So how much a window should be, it all depends on your data and your kind of like a choice. So there's no kind of best window over there. Okay. So now I guess I'll hand over to Wang Yu for the next part here.
Oh, I forgot to unmute myself. Can you hear me now? Okay. Well, now I will talk about the rest part of the smoothing, exponential smoothing, double exponential smoothing, and triple exponential smoothing. As Daniel said and Tempe said, actually, like those smoothing skills are used to not only used in prediction, also used to estimate the trends in the like in the absence of a seasonality. Like here, I want to mention one point that in like in the time series model, usually we have several components. The first component is like the trend. The second is seasonality, and the third is the noise, like those stationary things. So why we do exponential smoothing, here when we don't have much synchronality, we could use this method to estimate the general trend that if the curve is smooth enough, we eliminated the noise, and we could see the general trend of this time series data. So let's start from exponential smoothing. Here we can see we could use this function and to predict the data. Here we use compared to the models, the moving average, we added the alpha parameter and the f. And why is this called exponential smoothing? I would like to share you another screen. Oh, it is. Let's see. I cannot see my screen here. Okay, second. Share. Oh, here. Here is the function. We based on the first this function, and this is a recurrent function, right? So after, if we give y1 and if we set y1 head equals y1, then the yt head will be in this form. This is actually an exponential function that we can see here. Actually, if we want to estimate yt, and we need the data from y1 to y2 to yt minus 1. And here we can see that if we take alpha smaller enough, and mostly the yt head will be yt head will be affected by the previous data, and that means the weight, this is the weighted moving average of t minus 1 to y1, and those weights are decreasing exponentially. So I think so here yt minus 1 had the heaviest weight, and the far the data, the weight is lower, so it seems more reasonable than just a moving average here. So let me share my screen, this screen. Okay. So here in this model, we need to find which is the best parameter alpha, and this depends on here we can use a statistic technical to optimize the value of alpha, where we could use this square to determine the value of alpha, or we could use our knowledge to select the alpha. So here is the function defined for exponential smoothing. It's very simple, and this is the argument. First argument is the data series, and the second one is the alpha. And so we could do iteratively from 1 to the series length, and but here we need to first we set the y1. So here the y1 head equal, we set as y1 the real value, and then this function is used to plot the exponential smoothing. And here we use the as data here, and we input 2 alpha. From the alpha, we can see if we use 0.05, you can see it's smoother than the alpha equals 0.3. That means the alpha is smaller, the smoother the curve is, and then you can better see the trends because we eliminate most of the noise. And this plot shows the does my screen this screen too small? Oh, okay. This is another data set use the current, and we use the 0.3 and 0.05. We can see this is much smoother than we use 0.3, and so this is a exponential average smoothing. And I want to mention another point here while using the exponential smoothing. So here we could choose different initial value of one y1 head. Just I used the y1, the real value, the data, and I could always also use y, like the average of y1 to y4, and here, as I before mentioned, the choose alpha value, which is we could as a MSE, and we could use a Markov procedure, but I didn't cover here, but you can find it on Google. And another problem of the exponential smoothing is that it's like the moving average. It can only predict a single point. So here we introduced another method called double exponential smoothing. Here, the major idea of this method is to we decompose the series data into 2 components. First, the intercept, it's called level, and the second part is the slope. So you can predict the larger trend of this theory. Here, the idea is similar to exponential smoothing. For the slope, the slope, we estimate the slope from the previous slope data from bx1, b1, b2 to bx minus 1. Oh, okay. Oh, sorry about that. Oh, okay. Is that good now? Can you see the formula? Yeah. Okay. So here is the 2 components of the double exponential smoothing. The first one is similar to the previous one. We use alpha here, and this is the intercept. And this one is the previous intercept. And the slope here, we use the similar idea that for the slope, we estimate from the previous slopes like b1, b2 to bx minus 1. And now the predicted value will be sum of 2 components. One component is the level intercept, and the other one is the slope. They plus together will give you the predicted value. And so the prediction is this one. So here we give the function to get this double exponential smoothing. And here there are several arguments. First one is the data series, and the second one is the alpha, beta. And here I want to mention that both alpha and beta should be within 0 to 1. And here we use a for loop to generate this the prediction. If n equals 1, here we can see we just use the first observer value and the first observer slope. And if n larger than the length series, we use the last result. Otherwise, we input those two formula into this function, then we could get the result, and this function defines the plot of the double exponential smoothing. And here we use this function. We input adverse data, and we input two alpha and two betas. We could see that when the alpha and beta is very small, it smooths well enough. But here it's a little bit different from the single exponential smoothing method. When alpha is smaller, the smoother or the better the fitting up. But here we need to use the other method to optimize the mean square root error of the data. So I will introduce with the cross validation part here later. And here I use the same parameter here, 0.9, 0.02, and 0.9, 0.02. They give different results, and here it's quite different. You see that if we took 0.02, 0.02 for beta, it's quite it's not easy to interpret. No, so so the next part is the triple exponential smoothing. It's also called a hot winters method. Here, as we said, there are, for those time series data, many data have seasonality. So, but in the double exponential method, we didn't consider the seasonality factor, and also that method cannot be used in those data have seasonality. So here we add another factor, like other component to better model those data with seasonality. It's also similar ideas from the double exponential smoothing or exponential smoothing. We split the data into three components. The first component is like baseline, the intercept. The second one is the trend, and the third one is the seasonal things. That means, for example, when you got predict a series of data that if you use double smoothing, you can get the intercept and the slope. But here, if there's a seasonality for each year, you have up times, down times. In double exponential model, you cannot show that. Here we add seasonal components, so we could add this component into our model so we can repeat the seasonal characteristics here. Like the prediction, we will have three components. First is the level. The second is like the slope, and the third will be the seasonal component. And here in this model, you have three parameter need to estimate. First is alpha, second is beta, and third one is gamma. And you need to set the initial value for your your slope, your intercept, and your signal. Usually, you need to let's see. If a season is 7 days, the initial value for the season data you probably need to have from on the day 1, day 2, day 3 to day 7. Then you can do the prediction. And here we give the confidential interval, and this one is the prediction deviation, and this deviation also defined in exponential way. So later we will see why the predictor deviation in this method is good. And here, because this method is a little bit complicated than previous two, so here we use define the class. We input data and we define the length of a season, and we have our alpha, beta, gamma parameters, and we have prediction horizon and a scaling factor here. And this part I won't go to detail, but we will use the results later, and I will explain it a little bit later. And so the next part is the time series cross-validation. This is not unusual here because we in time series data we have to choose the loss function, and then we will using cross-validation evaluate our chosen loss function for the given model parameters, and calculate the gradient, and then we adjust the model parameters, and then we will find the optimized parameters. But here the difference is that in other cross validations, we have key fold of we classify the data into k fold. We can use k-1 as a train data, and another one as a testing data. But in time series, when you what we can do is separate into 3 folds. We use the first a group of data as a training data. Then we predict we predict the next data or the next should be t plus n
steps.
Yeah, t plus n steps. Here I saw another article, usually 5 to 10. And then here the difference is that here you cannot select a random data to be a training set. You have to follow the time stamps you shows like this graph. You should select more and more training data, then generate the test. And this function is the defined time series cross validation function. Like here we can, here use the split into 3, and this part is iteration over folds and training model on each focus and calculate error. And this part is we use the time series cross validation function, and we optimize the function. Then we generate the value. Here is for the, I think for advertisement set data set. We get alpha, beta, and gamma here. We can see here all those parameters are very small. And here is the, we defined the plot of this triple exponential smoothing model. And here I won't go to detail. And here they defined the plot, how to plot the anomalies and plot the intervals. It's a little bit similar like the moving average. And so here, like if we use the as data, we could get a very good fitted curve, and we could set the data you want to, how much data you want to predict. Here there's a 50 data to predict. It looks better than double exponential smoothing method. And here we can choose to plot the anomalies and to plot the intervals. We can see here some anomalies, and then another interesting thing here, from the plot of the predicted deviation, we can see that the prediction deviation sometimes changes very quickly, sharply, respond to the changes in the structure of the series, but then they will quickly return to the deviation and to the normal value. So this model is, I think, is good for anomaly detection, because they just forgot the past data, and this is an I think this is because the definition of predicted deviation here is similar to the exponential smoothing function here. The predicted deviation were more affected by the data, the data more close to them, so they will easily to forget the previous the deviation happened longer ago. So so the next is the estimate the parameter of current data. It's similar as the previous advertisement data. We use the same function to estimate the alpha, beta, and gamma. Then we plot it here. This is a nice trend, and you can select how many more data you want to predict here. And here you can also show the intervals and anomalies. You can detect those kind of anomalies. And here is the predicted deviation. So these are my part. Do you have any questions? for single, they have some. Yeah, I think all the I could show you this one. Share you it. You can you can see from this function when you want to estimate a t, and you can see here is yt minus j. That means you have summed the y2, y3 to yt minus 1. Yeah, so all have the weights, but I think y1, y2 will have very small. Yeah, same thing. Yeah, they all have weights for double and triple exponential smoothing method.
Hey, well, can you hear me?
Yeah.
Yeah, I have a little question about the cross-validation. I think we need to go back to the cross-validation page. There's little plot. Yeah.
Yeah,
that's one. So I don't know if I understand it or not. So basically, the cross-validation is like you use a small chunk of training data and a small chunk of testing data. You optimize the coefficients alpha, beta, gamma. Then you use the. So I don't know how did it work here. Then you apparently you use the whole chunk of training and tested data we already cross-fitted. Then you you use all those data to train the model again with the parameter you just got from the previous step. Then you I don't know. I don't get it. Like you already get the coefficient for a previous step. So when you put all the data into the training again, so apparently it's gonna change the coefficient. So I don't know. So my question is, why don't we just go straight to the, to the second step instead of have go through the first step if you have to change the coefficient anyway? So I mean, like, what is the point of here? Like, did I explain?
Yeah.
Did I express it?
Yeah. But I think I haven't go deep into this part. I probably need to more time to figure out and answer your question. Probably Daniel.
I think here, Brandon's question is really great. So first of all, if you just do the second step directly without this kind of gradual learning, you're probably gonna have overfitting problem. So if you just do this, if you just do the last kind of like a graph here, just split it once, then you do the training and the test, then probably you're gonna get a coefficient which is very overfitting. But if you do the gradual, this is like a sequential learning. You kind of learn the coefficient a little bit, then improve a little bit, then improve a little bit. So it's like slow learning move. In that way, you can average out all the coefficients so that you can actually get a better kind of coefficient over here. And again, just like what I said here, it's kind of like a slow learning, kind of like a kind of movement over there. So in this kind of movement, you cannot look improving your previous coefficient by learning the new data. So I guess that's the idea for the cross-validation right here.
Welcome. Thank you, Daniel.
Test convergence. No, it's not about. It's actually not about convergence. It's actually. So this is not stationary yet. So we don't know if this is stationary or non-stationary data set yet. So this is basically try to get a better prediction. So we're not trying to actually make the test data actually converge. This is not our goal. What we try to get is we try to make sure that the test data set, like the prediction we make, actually align with the test data set. They don't have a lot of difference. If that's a converge you were talking about, yeah, then yes. So basically you were trying to push your kind of like a prediction as close as it can to the real kind of like a, kind of like the Y or the data set over here.
Okay, I will hand back to Daniel.
All right, thank you to Wang Yu for this part. So this basically, I think this is very important part. Again, I just want to make some kind of tiny note on top of his lecture here. So you might be kind of confusing, like, oh, we have the rolling mean, we have the weighted average, now we have exponential smoothing. What's the relationship between all those kind of techniques? So first of all, they are all prediction techniques. So as you can see, what we try to do is always try to predict the YT here, or YT plus one, so on and so forth. So all the previous kind of like, all the kind of techniques actually have one common assumption. That is the future Y totally depends on the current Y. That's also why we actually use cross-validation kind of gradual learning here. That is, I guess, this amplitude part totally depends on this part. This amplitude part totally depends on this part. That part depends on this part. So back to Brandon's question, that's why we kind of pushing the boundaries further. So this is based on the assumption that we actually use the past Y to predict the future Y. That's exactly why we actually use this cross-validation techniques here. So all the exponential can smoothing, triple, double, or average, or like prediction techniques. Okay. Second of all, the rolling mean, the weighted average, the exponential smoothing are also a smoothing techniques. So it can also kind of like smooth the graph so that we can see the peaks and the bottoms very clearly. We can see the patterns very clearly. So basically, they all serve for two purposes. One for prediction, second for the smoothing. Okay. So for the exponential, so what's the difference between the exponential double and triple? So for the exponential kind of smoothing here, we basically only try to predict the Y. So basically, what we have here, the original model, like actually from this is that we assume that, for example, let me just do this. We assume that YT plus 1 equal to beta YT. Okay. So basically, we're assuming this. We're assuming like the future data set totally depend on the past or the previous time period YT. Okay. So we don't have a slope. We only have the slope here. We only have the slope here. We don't have an intercept. So that's the exponential smoothing. So if you look at the formula here, current YT totally depend on itself and past, a one-time period, one lag of the YT itself. Okay. So we don't have intercept. We only have the beta, right? We only have the beta here. But if you actually move to this part, if you move to double exponential smoothing, so this part totally changed. Basically, we don't have this model again. We have another model that is YT plus 1 equals to intercept, let's call it intercept, plus beta YT. So basically, now I add an intercept into the prediction. I do not just only want to predict the trend, the beta here. I also want to predict the intercept here. If that's the case, then use a double exponential smoothing. See, that's what we got. Intercept plus a trend. Okay, so basically it's based on this linear model. But if you look into the third model, like a triple exponential smoothing here, we have additional. We actually have additional. Let's go. It's right here. We actually have additional, like a third kind of component here, which is a seasonality here. So basically, you add another kind of component on top of this plus seasonality. Okay, so that is, we do not only care about the intercept, we care about the slope. We also care about the seasonality. So if we try to combine all three together, then that's a triple smoothing here. Okay, so which one to use totally depends on your assumption. If you think your kind of like a model it's just this structure, then you just use a regular smoothing. If you think it's this structure, use the second one. If you think there's some kind of seasonality inside, then probably you should use a triple exponential smoothing. Okay, so basically that's the difference between all three, and a little bit of summary on that. Any question about that part? All good? Does C validation optimize T as well? Cross validation optimize T. What is T here, Brandon? Seasonal. Okay, so the cross validation can be used for all the previous techniques. It depends on which kind of model you try to use. So if you try to apply this to the triple exponential smoothing here, what it try to optimize is so the loss function is still ordinary least square. So it's still like, I'm gonna do, so let's write in this way. So basically the model is y, oops, I'm gonna write here. Yt plus 1 equal to intercept plus beta yt plus seasonality. Okay, so basically that's actually the model we try to use. This is like the elementary kind of model we try to use with like triple exponential here. So what a cross validation try to do is always try to minimize 1 over n summation of y hat t yt hat square yt hat minus this is really hard, yt minus yt hat square. Okay, so basically all the cross validation, it depends on your loss function. So if we define the loss function on ordinary least square, then cross validation try to optimize this, try to minimize this. Then we can get a best coefficient or best intercept, best beta, and best seasonality. Okay, so basically we try to optimize this, make the first differential with respect to all 3, 1, 2, 3 parameters here, and then just like gradient descent, we try to find the best kind of parameters here, best intercept, slope, and seasonality. So basically that's my answer to the question. Any other question here? Okay, so I actually have a question for you guys. For the cross validation here, why not just we use this? Why not just just import from sklearn data selection import train test split? Why not just use this? Why not just use the train test split to split the data for the cross validation? Or why not just use k-fold? Any idea? Why we actually use a special function for the time kind of like train test split? Why not just use the previous conventional one we had before?
I can give it a try. I guess it's because all the data are related with previous data, so you can't really randomly pick 1/3 of the data from all the series and do projection. That's just not going to work because.
Exactly. Yeah, I think Brandon's right. So basically, those two functions is try to randomly divide the data, randomly divide the data, right? So, but each data comes with a timestamp. If you try to randomly divide the data and make it a prediction, it's gonna be chaos. Maybe you jump, forward to the date of July 21st. Then you jump back to the date of July 2nd. Then you try to make like a prediction on July 2nd using July 21st. It doesn't make any sense. So basically, we actually all try to make it a prediction using a past kind of like a data set. So basically, that means all those kind of like a library you cannot use for this. Basically, you have to follow the timestamps and try to make the division according to the time. Okay, so make sure you take that, and memorize that firmly when you make the cross validation. Don't use test split, test train split, or k-fold. It doesn't work for time series here. Okay, so that's this part here. So again, for all the smoothing, for the triple, double, and regular, yes, time dependence. So everything is like a time dependent. So you cannot just like randomly divide that because you are going to mess up with the time label over there. Okay, so I want to actually highlight this kind of graph a little bit. So basically, for all the techniques you had previously, triple, double, regular, weighted average, and smoothing, everything, you have to draw the confidence interval here. Okay, again, this is try to test whether your model works or not. Okay, it's try to test if the model works or not. If you have a lot of like those kind of points here, you have a lot of points like this, then probably it's not going to work. So this just give you kind of rough kind of way to think about, oh, the point actually just is either a lot of point lies out of a confidence interval. Should we actually reject the null hypothesis or not? Okay, so this is not very precise one. If you want, you can actually do a t-test, which I think it's gonna show later. Right in here. Yeah, basically you can use the z-test or t-test here, which I'm gonna introduce later, and see the p-values here for each kind of like kind of data points here, and try each kind of variables here, and try to see whether they're significant or not. Okay, so if you want a more precise one, you better just use like a test. Try to find the p-value instead of using graph. But this graph just gives you some kind of like a really kind of rough guess whether this model is going to work or not. Okay. So now I'm going to move to the third part, which is econometric approach here. So this part deals with a really, really important problem, which is called stationary, okay, or stationarity here. Okay. So what do we mean by stationary? So if you look at a graph here, this graph is called stationary, and this graph is called non-stationary. What's the difference between the two? As you can see here, oh, this graph, it seems like the mean, the average is, always on this horizontal line here. But for that one, the mean is kind of like increasing all the time. Okay, so one way to tell it's stationary or not stationary is the mean of the whole process the same, consistent over time, or it depends on the time. So this one totally depends on the time. With the time increasing, the mean is getting large. For this one, it's not stationary. The second way to actually test whether it's a stationary kind of like process is whether the variance is the same or is constant over time. For this one, oh, the bandwidth is pretty much the same, and the spread is pretty much the same. But for this one, oh, it's getting small and getting larger and larger and larger. So this one it's not converging, at least I shouldn't say converging. It's actually diverging here. So basically, you can see the variance is getting larger and larger. It depends on the time as well. So this is non-stationary. For this one here, again, this part is quite kind of like congested, quite compressed. So this one would have a small variance, but for this part, it will have large variance. So the variance here is still not kind of like the same across the time. So basically, the formal definition is some kind of statistical properties over time doesn't change, like in the mean of the variance. If that's the case, then the process or this kind of y is stationary. Okay. So why do we care about stationary? I mean, for example, if we have this kind of like graph here, if it's non-stationary, if you have the data point here, if you use the past data point, all the data point here, actually. So suppose we try to predict we try to predict a data point here. Okay. And if we have all this kind of positive data set, we try to predict a data point here. That's a bad example. Leave here. Let's do this. So we try to make a prediction here. Okay, we try to make a prediction here, and we have all the data set, previous data set here up to this point here. Then probably, according to this kind of like a wave here, you're probably gonna make a prediction like the y is gonna be here. It's pretty much the same height as that one here. But if it's non-stationary, then the y can go up here, or it can go up here, or can go lower than here. Okay, so basically it becomes non-predictable. It becomes non-predictable. For this one, it's predictable because if you have this data point, you can predict the next one, this one, that one, even this one, which have the same kind of peak as that one. So everything is predictable. If it's non-stationary here, it's not predictable anymore. So basically, you cannot make prediction anymore. So that's why we care about the prediction. We care about the stationary process here. Okay. So that's this part here. So now, how do we actually test whether it's stationary or not? How do we test it's non-stationary or stationary here? So basically, there's a formal definition for the stationary or the non-stationary kind of process here. Okay. So for example, if we have this kind of process, xt equal to rho times xt minus 1 plus et. So xt is the data point in current time period. This is the data point in the previous time period. And et is just like a y noise, or is actually a random process that follows normal distribution here. Okay. So now let's do a little bit kind of math here. So if we just do it again, do xt minus 1, it would be the same as rho xt minus 2 plus et minus 1 here. Okay. So if we combine the two kind of equations here, replace this right here, then we get this xt equal to rho squared xt minus 2 plus rho et minus 1 plus et. Okay. So we can keep doing that until we reach x0, until we reach back to the previous, the final kind of like, kind of data points here. So if we do that, the variance of xt would be sigma squared times this, This would be arithmetic, kind of like a sequence here. So basically the ratio between every two terms is rho here. So if you do this, if you actually try to calculate that, it's going to be this. It's going to be that. And if n equals 2 or goes to infinity, we're going to have this. Okay, we're going to have this. Okay, so keep that in mind. Okay, keep that in mind. So now, if rho equal to 1, if this rho equal to 1, we would have xt equal to xt minus 2 plus, et minus 1 plus et. So the variance would be t times, sigma squared. Now the problem appears. The variance of xt depends on t. So what we want is a variance doesn't depend on t. We want it to be consistent over all the time period. But now, if t is 1, it's going to be sigma squared. T equal to 2, take sigma squared. If t equal to 100, it's going to be 100 sigma squared. That basically is telling you that your x is going to be like this. It's going to spread out. If that's the case, there's no way you can predict the future x. There's no way you can predict the future x. Okay, so if that's the case, we call this case rho equal to 1. We call that as random walk. Okay, so basically, let's go back to. Okay, so random walk is that this case is a case that xt equal to xt minus 1 plus et. Okay, so that is when rho equal to 1. When rho equal to 1. Okay, now let's go back to the case where rho doesn't equal to 1. So the variance here will be this. The variance here will be, sorry, that should be, I made a mistake. There should be a sigma square here as well. Okay, 1 over rho times sigma square. Now, if rho getting larger, if the row is getting bigger and bigger, what's going to happen to the variance of xt here? That's a question for you guys. What do you think? Like, if rho is actually increasing, what's going to happen to the variance of this? Is the variance going to increase or decrease? Yes, it's going to increase over time. It's going to increase over time. If it's actually increasing over time, do we have a stationary process or non-stationary process? That is, we don't have any stationary process yet anymore. Okay, so basically, what we don't want is that we don't want a row to increase. We want a really small row. We don't want a row to be large. That is, the greater row is, the more the closer the row equal to 1, the severe this kind of problem we're going to have. Okay, the more non-stochastic this process can be. Okay, so that's an important takeaway here. So basically, what I'm seeing here is, if you have this kind of equation here, if you try to make a prediction of future x, based on your future x based on your past x, and if you have the row here, you better do a regression, see how large that is. If this is 0.9, that means you are having a trouble with this kind of problem. That means pretty much like all your predictions not accurate at all. Okay, so that's this part here. So how do we test whether it has stationary or it has a random walk problem or non-random walk problem? Okay, so before that, I want to talk about a little bit more on the random walk. So random walk sometimes is also called a unit root problem in linear regression. Basically, is this kind of process here, just like what we had before, and a row equal to 1. Okay, so if row equal to 1, we would say the root of the equation is 1. So unit root is random walk. Okay, unit root is random walk. So if we have a random walk problem, we have a unit root problem. How do we solve the problem? So there's a really simple case we can actually test whether we have the problem or not. So that is, you can subtract the equation here, xt minus 1 from both sides of the equation here, of this equation here. Then you're going to have xt minus 1 rho minus 1 xt minus 1 plus et. Now, if rho equal to 1, that means this part will be 0. What does that mean? That means the coefficient of xt minus 1 is not significant anymore. So basically, what we do here is we try to generate this equation. We get a coefficient. We do a t-test or z-test on the coefficient. Test whether it equal to 0 or not. Okay. So that's basically called the decay, or we call it like a df, DQ folder task here for the random walk. And this xt minus 1, that is, you subtract the previous just one time period lag from the current time period x, is called the first difference. Okay. So that's a random walk and unit root or stationary process. Any question here? If you don't have any question, let's move forward. Okay. So, okay, since we have the stationary problem, this part tells us how do we actually solve the stationary problem. So we actually going to have this kind of model here, SARRMA model, which is actually called autocorrelation. I think it's seasonal autocorrelation and moving average kind of like a model for a time series here. Maybe Joyce, you know more about this model, like how do we use the model? But I'm just going to give you guys kind of like introduction how we're going to use the model here. Okay, so before that, I just want to introduce the two kind of like concept here because we're going to use this later. The first is called autocorrelation. Okay, autocorrelation. So if we have the autocorrelation between yt, or if we have some kind of correlation between yt and yt minus j, or that is, we have some kind of correlation between current y and all previous y. then we are sad that we have some autocorrelation process. Okay, so we can actually calculate the correlation between each kind of like a y over there. So basically, if we try to calculate the correlation between yt and yt minus 1, we can do this. So this formula here is autocorrelation function. That function tells us how much correlation do we have for the yt and the yt minus j. Okay, that is how bigger the rho gonna be. The rho we had previously. Is it gonna be 0.5 or it's gonna be 1? Okay, so that's basically the autocorrelation function. So that's one way to actually test whether we have the stationary process or not. Second way to test it is, except for the df like a test, is we can use a partial autocorrelation here, which is called PACF. Okay, so partial autocorrelation basically is you make a regression of y on all previous y. Then each of the coefficient here is called a partial autocorrelation factor. For example, this is a partial coefficient. Rho 1 is a partial coefficient or an autocorrelation factor between yt minus 1 and yt. So there is a fundamental difference between the two. For this one, we don't use any regression. We just calculate covariance directly. And this is how we calculate covariance. Now for this one here, partial autocorrelation basically is conditional on all the other yt's, and then I try to extract the correlation between yt and yt minus 1. Okay, so with this kind of concept, now we can actually build this kind of model here. Okay, so basically what we try to do is, first of all, we try to plot the time series. We try to plot all the the numbers of advertisement watched for every single hour. Then we try to plot the autocorrelation graph and a partial autocorrelation graph, and try to see what kind of pattern the data show us. So there's a lot of stuff going on here. So I just want to point out several kind of important part. So basically, this is try to make a panel for the different kind of plots here. So subplot to grid here, basically it try to make a subplot. So basically this whole function here absorb 3 kind of argument. First of argument is what's the layout. So for this one, we want a 2 by 2 kind of graph. That is 1, 2, 3, 4, 2 by 2, 2 column, 2 row kind of graph here. Since the first kind of graph is really big, so we want 2 by 2 here. So you first have to tell them what kind of layout you want for the graph. And second, what's the position of the first graph? The position for the first graph is the first row, first column. Second, the last part is like, do you want the color to span across all the columns? Do you want to actually it covers all the columns right here? And the answer is, yes, I want to actually cover all the columns here. So this one here, again, is the same. So basically, this is a time series graph. This is an autocorrelation graph. That's a partial autocorrelation graph. Okay. So we also have the p-value here. Okay. So what is the p-value? The p-value here is the DK Folder test we have. So basically, if you want to get that test, and if you want to get a p-value, you can do this. So we import this kind of model, SM, stats models, TSA, stat tools, then add folder. Okay, add folder. Then you put the variable you will try to test here, and the first kind of component here, the index, the component with the index 1 here is a p-value. So I'm going to show you. This is really useful kind of like function. Probably going to use many times. So it has a lot of kind of like output here. So first of all, it returns the test statistics. Second of all, that's our first component. Second component, p-value, and it also have some kind of critical value here, and a dummy class with result catch attributes here. So basically, what we care about is just this. So that's why we just add 1 here. We just want a p-value here. Okay, so that's a p-value. Then we're going to plot the autocorrelation. So there's one kind of automatic autocorrelation prediction here. That is SMT graphics plot ACF. Okay, so the plot ACF just plot autocorrelation here. What do you need to put inside is y, which kind of data you want to plot autocorrelation. how many legs you want. How many legs you want. Do you want autocorrelation? Because if you go back here, how many J do you want here? Do you want a YT and a YT minus 1, or a YT minus 2, or YT minus 40? Okay, so you have to tell them, the function how many legs you want. So here could be 20, 40, it depends on you. And here, which position do you want to fix? Which position do you want to fix the graph to? So this is the position of the ACF graph. So we want to fix the position to that. So we make the axis equal to that. Same happened here for P plot P ACF here. Okay. So after the plot, we're going to have this. So this is time series we had previously, which is the same. And this is autocorrelation. That's a partial autocorrelation here. So as you can see here, P value equal to 0. If P value equal to 0, now the question is, my question for you guys is that, do we have a random walk problem or not? If P equal to 0, do we have random walk problem or not? Yes, if P equal to 0, basically we don't have random walk problem anymore, okay? But now the question is this the final answer we can get from here? Is that everything we can do? Actually, no, this p-value is not trustable. This p-value is not trustable. If you look at autocorrelation here, what can you say? Oh, for the first 5 hours, positive correlation, negative, positive, negative, positive. What is this? A partial correlation doesn't tell us a lot, too much. What about this one here? What can you see from this graph? Any idea? Just one word. You can see one thing from this graph. I think someone just mentioned that. Did you guys see some kind of seasonality here? So seasonality every 5 hours. So here, every 10 hours actually. It goes up, down, up, down, up, down, up. So that means we have some kind of seasonality going on right here. So basically, it doesn't actually expect any kind of random walk process because of the seasonality. Because some people actually try to watch it as at weekends. So at weekends or at night, the correlation becomes positive. But on the daytime, it becomes kind of like a negative again. So if that's the case, we shouldn't be happy about this process. That's basically saying like, oh, you don't have the random walk just because you have the seasonality. But if you get rid of the seasonality, you're probably going to have the random walk problem again. Okay, so that's what we're going to do next. We try to eliminate the seasonality here. We try to eliminate the seasonality here and try to see whether we still have the random walk or not after we eliminate the seasonality here. Okay, so the seasonality, as you can see here, is pretty much like 24 hours is for the day. So what do we do here is we try to actually, make a drift, or we try to subtract. We try to shift everything by 24 hours. Okay, so basically what do we do here is we take the seasonal difference, which means the simple subtraction of the series from itself with a lag equal to seasonal period. So for this one here, as you can see, this is day 13th, that's the 14th, right? So that's a day. Oh, 14th to 15th, again, that's a day. 15th to 16th, a day. If you look at each day, the pattern is pretty much the same. So we have actually a daily kind of seasonality here. So we try to subtract 24 hours. Okay, so after we subtract that, we subtract the seasonality pattern here, we can plot it again. Oh, now you can see that P is actually not 0. It's actually about like 4%, very close to 5%. Okay, very close to 5% here. So in this case, if you look at this graph here, do we have a stationary process or not? If you have this P, you have this graph, and you have this graph, that graph. Are you going to say this is stationary or not? That is, the mean and variance of the S watch doesn't change. What do you guys think? Yes or no? Do we have a stationary process here? Or we have non-stationary process for this graph here? What do you think, Lin? What kind of problem do we have for autocorrelation, partial autocorrelation? Not really. Actually, we don't have any kind of big problems with autocorrelation or partial autocorrelation. But we have a problem with this. If you look at this, it seems like it's increasing, then decreasing. The mean doesn't actually, kind of like stable at 0. And also the variance is kind of converging sometimes, then it's kind of diverging, then converge. So that means this, and also the p-value is really close 5%. So basically that is saying like, oh, we don't really have a stationary process. Okay. The mean is changing, variance is changing, and the test is not passed. We didn't pass the test. So what can we do? So what we do here is we try to make the first difference. Okay. So why would we make the first difference? Since we don't have a stationary kind of process, that means the rho is going to equal to 1. So we're going to subtract an xt or minus 1 from xt. We make the first order difference. Then this part will be 0. The other part will be 0. Basically, we're left with et here. And if et is actually a normal distribution, what's the mean of et? The mean of the et here is going to be 0, because we assume that this is a normal distribution. So let's do this. We subtract one time period, one lag from the original time period. Now we plot it again. See, it becomes much more stationary than before, and p-value is 0. So now it's kind of like the mean is around 0, and variance doesn't change too much from the previous process. Okay. So basically what do we do here? First step, try to plot the original graph and see whether there's a seasonality pattern. If there's a seasonality pattern, try to figure out what's a seasonality pattern. It's a day pattern, month pattern, or week pattern. If that's the case, subtract the pattern, then plot the graph again and look at the pattern here itself and look at the p-value. If the p-value is really close to 5%, that means we didn't pass the test. Then we're going to do the first order difference. If the first order difference doesn't pass the test, then we do the second order, so on and so forth. Okay, so that's basically how we solve the stationary process right here. But this is just specifically to this case. Like it doesn't actually quite apply to other cases. All depends on what kind of data you have. Okay. All right. Here comes like hardest part, which is called ARIMA or SARIMA. Okay. So SARIMA has three important kind of parts here. Which the first part is called AR. So autocorrelation model, which is AR here as AR. Autocorrelation model. So basically, it's a regression of the time series onto itself. Basically, regress YT on YT minus 1, so on and so forth. Okay. So the basic assumption is that the current series value depends on the previous values with some lags. So basically, the model is going to be YT equal to beta 0, YT minus 1 plus beta 1, YT minus 2, so on and so forth, until you reach YT equal to 0. Okay. So the maximum lag in the model refers as P. Okay. Keep that in mind. So the maximum lags is how many kind of time period you want to go back is P here. So to determine initial P, you must look at this, the partial autocorrelation here, and find the biggest significant lag after which most other lags becomes insignificant. So what we mean here is we're going to do this process gradually. We're going to add YT minus 1 first. we don't add any other YT here, and try to look at the row. Is that significant or not? If it's significant, that means, yeah, we should add YT minus 1. Then we add another YT minus 2, and we look at its coefficient again. So we keep doing that until we reach a data point that we add another YT minus 1. We don't have a significant row anymore. We don't have a significant row anymore here, okay? So this can be seen from the partial autocorrelation, not autocorrelation, because autocorrelation doesn't do the regression, okay? So that's that part. So P is an important factor for autocorrelation here. MA here, moving average model, second part. So I'm not gonna go too much details right here, but the model basically is seeing like the error of the time series. Actually agree with this kind of assumption that current error depends on the previous previous kind of errors with time lags. So basically, we do not only care about Y, we also care about the E. So we are seeing like a ET depends on the ET minus 1, minus 2, so on and so forth. And Q is the maximum lags you can actually use for that kind of regression. So if you add those two together, we have R mod, okay, which is ARMA here. So a third part would be integration, because we have since we have autocorrelation problem here. So if we have this autocorrelation problem here, is if the row is closing to 1 or really big, then we have to do some kind of like first order difference, right? So that's order integration. Basically, you try to make YT minus 1 so that you get rid of the row here, just like this one here. So this is called I, or integration. Okay. So if you just do this, then that's a first order integration. But if you do xt minus 2, that's the second order integration. Okay. So that's how we define I here. So basically the D here is how much time difference do you want? Okay, how much time difference do you want here? Is it 1 period or 2 time period? There are several other kind of like important factors here. SS here, this is correspond to the seasonality. Okay, so basically S equals to the number of the season period, or the length of the season period. If you believe you have the daily kind of like seasonality, probably if your data set is in our kind of unit, then S should be 24. If you think it's 2-day kind of seasonality, it should be 48, so on and so forth. Okay. P here is order of autocorrelation for seasonal component of the model, which can be derived from PC ACF. Okay. So for example, if the time period equal to 24, if the seasonality equal to 24, and we see the 24th and 48th lags are significant in the ACF, we're going to say P equal to 2. I will show you guys later how do we define the P here. Basically, it's telling you what's the order of the seasonality matters here. Q is similar to P here, but we actually use the ACF to do that. Okay. So D is order of the signal integration. It can be 1 or 0. Depends on whether seasonal difference will apply or not. So this is YT minus 1. This would be the seasonality ST minus ST minus 1. Okay. So basically that's all the factors here. Okay. So now let's look at the final plot and try to figure out those parameters ourselves. So this is the previous plot that we had before. So if you look at, so first of all, let's look at a P here. So again, P here is how many of maximum number of lags in the time period. So we need to look at PACF. So the P equal should be 4 because after 1, 0, 1, 2, 3, 4, you didn't see too much significant rows, significant coefficient between YT and YT minus 1 here. So although there are 1, 2, 3, 4, 5, 6, like a little bit, most of them are just like non-significant at all. So that is here we're gonna make the cutoff right here equal to 4. Okay, that is after this data point here. Oh, sorry, let's go back to. That is after this data point here, this one here, fourth one, 1, 2, 3, 4, this one here, we don't actually see any significant lags show up anymore. Okay, so D is 1 here because we made a first order difference. So that is, we did this. Okay, we made a first order difference here. So D equal to 1. Okay, that is, what's the integration here? Okay. The next part will be Q. The Q would be around 4 as well. That is, if you look at the autocorrelation here, also 1, 2, 3, 4. After 4, you doesn't see too much kind of significance over there. Okay, so Q is also 4 here. The P, the capital P here would be 2. So why would it be 2? So the P here is what's the order of the signality. So if you look at this graph, PACF, that's how we define the P here. This is almost like a 24. So this is very significant. If you do it again for 48, oh, we have 2 significant or 3 significant here. So we have 1 significant at 24th hour, another significant at 48 hours. So I would say, oh, P here is equal to 2. That is, we have 2 order kind of like seasonality here. So it's actually 1 day and 2 day here. Okay, D equal to 1 because we actually did 1 seasonality difference. That is, we only did it like a 24. We didn't do 48. Okay, we didn't do 48. And Q is 1 here because we only have 24 as significant one. 48th one is not significant at all. So this part might be confusing. I will just pause here for a second in case you guys have any question here. So feel free to ask any question here if you guys are kind of confused about these kind of parameters here. Nope, okay. So the next part would be building the model. Okay, so now we already know the parameters. We already know the parameters we need. Now let's build a model. So this is just a kind of try. We try to set what kind of parameters. We figure out, oh, those parameters could be the excellent, kind of choice here. But what if we just want to find the best one? We don't know whether this is the best one or not. So we're gonna, list out all the parameters here, P, D, Q, capital P, D, Q here. And we actually give each of them some kind of like, parameters here, a parameter range. And we try to figure out which one is the best. So first of all, we are going to make it a product of all the parameters here. Okay. So basically, if you do the product function, it's going to do all the combinations between P, S, Q, S, P, S, Q, S here. So what are you going to have is this. Okay. This is just our first 5. So 2 to 5 times 2 to 5, you are going to have 2, 2, 2, 3, 2, 4, 2, 5, so on and so forth. Different kind of combination over there. Okay. So we're going to use this as a parameter. Okay. And we're going to use it for the model and try to test whether we have the best kind of model or not. So what's the standard of testing whether we have the best model or not? So first of all, we're going to build a model. So how to build the Cerama kind of model here basically is SM, PSA, time series analysis, state space, ceramics here. So inside, you first of all have to put the data. Second of all, you have to tell the models the order. So what is the order here? The order here basically is P, D, and Q. Okay, is P, D, and Q. This is the first 3 parameters here. Okay, so we're gonna put, parameter list. This is a P, that's a D, that's a Q here. Seasonal order is this P, D, and Q, capital P, D, and Q here. So we put those 3 inside here and S. So then we're gonna phase the model, and we try to actually predict the AIC, which is one kind of scores try to test the model. If you want to know more details, you can actually, find more on the website, but I'm not going to go too detail for this. So basically, we try to find the minimum AIC across all the parameters. Okay, we try to find a model that with the lowest AIC here. So if you finish this kind of whole test, you are going to have this table. Okay, you're going to have this table. So this is the parameters we have, PQS, so on and so forth. This is the AIC, and this is the lowest one. Okay, that's the lowest one. So that is to say that we're going to have PQ here as 2311. That's a best parameter. Okay, so in that case, if that's a best parameter, we're going to put the best parameter again into the model and redo the model here. Okay, after that, we're going to have this kind of regression model. And we are going to have, because we only have 2P here, so we have L1 and L2, and we have 3Q here. So that's L1, L2, S3, MA, 2 AR, 3 MA, and 2 AR and 1 AR and 1 MA seasonality here. So if that's the case, this is all the coefficients, that's all the P here. Okay, so this is the final model you're going to have. Okay, so so this is just a plot of the best model we had here. So this is basically just plotting of this kind of model here. As you can see, P equal to 0, the whole process is quite stationary, and we don't have any kind of problem with autocorrelation and partial autocorrelation anymore. Okay. So yeah, so this is another kind of graph that is trying to plot the theorem based on the previous kind of actual kind of model. So the red line is actually the model here. The blue line is the actual model. So these two parts here is a prediction. Okay, so the gray area is a prediction. As you can see, the prediction very similar to the previous model. That's because we use autocorrelation. We basically, predict the future based on the previous, kind of like data points. And we have to make sure this is stationary. Okay, if that's not stationary, we cannot predict those two. Okay, so that's theorem model here. Okay, so. So next part would be the feature selection or feature extraction here. So since we only have one kind of data set, that is one kind of column, which is the number of advertisements we watch here. So we have to think about what kind of other features we can generate from that. For example, the window statistics, the max or mean value of series in a window, mean value in a window variance, and daytime, features, number, minute of hour of the day, day of the week, so on and so forth. Okay, so what do we do here is we try to extract all these kind of parameters and make a regression. Then we try to see which one is more important, and we eliminate the non-important one. So the first part is we actually make like a number of legs here. So the number of legs start from 6 until 24. So it's going to be t minus 6, t minus 7 until t minus 24 here. Okay. So as you can see here, y leg 6 until 24. Okay. So the next part would be we're trying to actually use all these kind of legs here and use the leg to make a linear prediction here. So this is how we do the cross-validation. Okay. So this is a standard process how we do the cross-validation. Don't use the train test split. Use this function. From sklearn model selection, you have to import time series split. Don't use those two. Okay, don't use those two here. Don't use that one. So you actually tell them, I just want 5 split. I just want 5 folder here. So inside this kind of function, we define a new function that we're going to split the train and test. So basically, this tells you the index of the training data and test the data over there. Okay, so then you use the test index from this one here, from this part here, use that to define the training and test the data set here. Okay, so after you have this, you can have the train test the data set, then you put that into a linear model. You put that into a linear model here. Let's see here. Yeah, you put that into a linear model here, and then you can do the regression. So after you finish the regression, we're going to plot everything here on the graph. So this is the blue line is the original kind of like a y. the green line is actually prediction, linear prediction here, and this is just confidence interval here. As you can see, the mean absolute error is like 5.86%, and the prediction is actually not bad. It actually follows pretty much close to the actual kind of data set. And this is just the importance of all kind of like a lags here. That's a coefficient of a lags here. Okay, basically 24th lag, has the biggest kind of like coefficient. That's normal because we have the delay seasonality over there. Okay, so the next part is what if we just try to add more? We try to add hour and day of the week, and try to add whether it's a weekend to use the regression, see whether that's going to improve the model or not. So after that, the mean absolute percentage error is 5.45%. Okay, so it improves a little bit, like from 5.86, it drops to 5.45. But if you look at the coefficient, 24th lag, the coefficient is over 50,000. So if that's the case, then we actually have an overfitting problem. That is, this is too much overfitting for this lag. That means the 24th kind of lag is actually performing too well. So if that's the case, we're going to do some kind of cross-validation. We're going to actually kind of regularization techniques try to get rid of that. So basically, what do we do here is, go back in here. So basically, first of all, we try to do regularization, and we try to find the correlation between all the lags here. Okay, so all the features here. After that, we actually try two kind of regularization, reach, CV, and lasso. So this is L2, and lasso is actually L1. L2 doesn't actually get rid of any coefficient, but L1 actually going to make the coefficient equal to 0. For this case, as you can see, the MAE is like actually 5.84%. So this is actually not very good because the original kind of model is 5.86. What about lasso? Actually improves quite a lot. If you use lasso, it's going to be 5.47% here. Okay, so basically that means you should choose lasso over the reach for this kind of model. So another try could be you can just use a boosting here. Use XGBoost, import from XGBoost, import XGBoost here. You just kind of like fit the X train and a Y train, and then you can get a score which is much lower. That is 3.76%. Okay. But generally speaking here, we don't actually recommend using XGBoost or any kind of boosting trees because for the time series, usually a linear prediction performs much better than the decision tree structure. Because the decision tree structure try to make, are you greater than this value or smaller than that value? We can split. But for the time series, you can barely do that. So I guess this is just an exceptional case for the decision tree model overperform like a linear model here. All right, that's pretty much everything. Just the last question here. For the XGBoost, so for the previous one here, as you can see, for all the models that we can predict, we can draw the coefficient here. But for the XGBoost, we didn't actually draw this graph. Why? Why not just draw the coefficient with XGBoost here? Why we only have this graph, not this graph for the XGBoost? Any idea here? Yes, so basically XGBoost is not a regression. You don't have a coefficient with XGBoost, okay? So don't make the silly mistake like, I'm gonna plot like coefficient like along with this graph. It's not gonna work because you don't have a coefficient with XGBoost. Coefficient only appears for linear regression, okay? So yeah, basically that's everything for today. I think the most important part is what Tianpei just mentioned over there, the smoothing, what Wang Yu just mentioned about the exponential smoothing, and this part, like ceramics here. Yeah. This is basically the number one, and also the most commonly used like time series model, you absolutely will use if you do a time series over there. Okay. So yes, basically, yes, absolutely right too. So basically P here, that's a good summary. Basically P here is how many legs you want for the Y. D here is how much difference do you want to do? Do you want to do first order difference for the Y or not? Q is, what's the kind of like, it's a number of legs, like a number of legs for the autocorrelation here. So that 3 is for the Y, and that 3 here is very similar to this, but for the seasonality. Yes, you're right. Yeah. So SERIMA is actually moving average plus seasonality plus autocorrelation plus first order difference or the integration. So basically covers everything. It's kind of like complex of everything. It covers all different kind of techniques. Try to make the model stationary and also precise for the prediction. Any other question? That's everything for today. Okay, Brandon. So this is the linear model good enough to predict stock price? That's a really great question. We actually tried it. Like me and my cohort, like students at my office, we actually tried. So yes, Lin said, like both of you are right. There's a lot of outliers. There's a lot of randomness over there. So you know what? According to my experience, what they try to do for the stock prediction is they try to eliminate all the randomness, make it stationary. You know what I mean? So pretty much like, previously you're gonna have this is stock price or that's a stock price. You try to eliminate all the randomness to make it like this. Then you make the difference. And then you make a prediction here. So you can only make the prediction. Remember that you can only make the prediction on stationary process. For non-stationary process, you can never make the prediction. It's never going to be precise. So basically, what they do for stock price prediction is like they have this data, they get rid of all this kind of like randomness and try to transform that into this, and then make this prediction. But this process of eliminating all the randomness is a huge amount of work. Like sometimes it probably doesn't work. All depends on, I guess, are you fortunate to have, those kind of like techniques and also the data to actually eliminate all the outliers over there. Yeah. Good question, by the way. But for some other time series predictions, for example, for the sales prediction, for the demand forecasting, yes, this could work because sales and demand forecasting have some kind of patterns, not that random. For example, the sales will increase in summer and will be lower in winter, right? So, or the prediction of the crime rate over time. Crime rate will be higher in the night and lower in the day. Yeah. Any other questions? No questions? Okay. Yeah, I guess that's everything for today. And thank you so much for listening. I know there's a lot to digest. Maybe I'm too wordy about this, but I just want to show you guys like all the pictures we have for this time series analysis. Of course, this is just like a tiny piece of the iceberg, across, the whole chapters. If you want to know more, there's in the notebook, there's actually a lot other use for resources in the last kind of like part, which I attached here. I think in the last part, where is it? Right here. Okay. So yeah, that's pretty much everything. So back to just one more second, sorry. Back to Brandon's question. If you want to do the stock price prediction, most of the time they don't use time series prediction. Most of the time they actually use this LSTM or deep learning. So that's going to be more precise than everything. Okay, that's everything for today. Hope you guys can, take care of yourself and wash your hands and, stay indoor and stay healthy. Okay. All right, see you guys next week.